Hi, welcome to polynomial regression session. Polynomial regression will be useful for the nonlinear data. When simple linear regression algorithm will perform better whenever we are using the uh, data is arranged in linear manner. That is, the relationship between the independent variable and the dependent variable is linear. If the data is non-linear, the linear regression fails to find best fit decision boundary. So here you look at that. This is the linear regression equation for given data. These are the data which are non-linearly arranged. So for the non-linear data, the decision boundary by using the linear regression is not creating the best fit line. So this is the issue created from the linear regression. For that, what we are doing, we are going to use a polynomial regression to perfectly create the best fit line. So based upon that, the equation is shows the curvilinear relationship between independent and dependent variables. Here the data is arranged in the nonlinear manner. The equation here it is given theta 0 x0 plus theta 1 x1 plus theta 2 x2 square. So polynomial degree is varying for each and every term. Again, it is depends upon the problem statement. In this equation, coefficient theta's degree is always 1. For theta, degree is always 1. The degree will be varying only for the feature values x. For the theta value, the degree always will be 1. That is the parameter we can update to optimize the model. So the theta value will be determined during building the model. The degree of order here used as a hyperparameter for the developing model. High degree of the polynomial tries to overfit with the given data set. At the same time, the smaller degree will try to underfit with the given data set. So we have to perform the trade-off between underfit and overfit between the bias and variance. This plot shows best fit decision boundary over the given training data and test data. Test data is indicated with the green color dots, and training data is indicated with the blue color dots. So when comparing this both plots, same kind of data, the single I mean simple linear regression is not creating the best fit line, best fit decision boundary, but polynomial regression creates best fit decision boundary. Here the polynomial regression is applied in Python by using the polynomial transformation and linear regression combination. First, we will convert that given data set into the polynomial terms using the degree of a polynomial equations. Here the degree is acting as a y-intercept in linear regression. So first we will use the define the degree for the given equation for to create the polynomial features. Then we are transforming the training samples into the polynomial features. Then after transforming, we will apply that transformed polynomial features into linear regression. So here the linear regression will create the decision boundary for polynomial features. Then based upon that, here that this both steps are combined together. The linear regression and polynomial features are combined together. That is called pipeline. So we are creating the pipeline for the polynomial transformation, I mean transformed features and linear regression. Then we will create the decision boundary by using the best fit line. Here how to select the optimal degree for polynomial equation. In the forward selection, we will increase the degree step by step until we are getting the optimal result. In backward selection, if you are getting overfit, then what we have to do, we have to decrease the degree of the given parameter until we are getting the optimal solutions. Why we are playing with the higher, I mean, degree of the polynomial equation, in the sense here the degree is acting as a hyperparameter in the polynomial regression. Here, the multivariable polynomial equation is given here. Theta 1 x1, theta 0 x0, theta 2 x2, and theta 3 x cube. So here the dimension of the equation is different. Dimension of the each and every feature is different. So we can apply the polynomial regression for many features in the given data. Here, if it is the case, we have to go for 3D plots. 3D plots. That's what given here. The loss function is estimated by using the each and every data point. For each data point, we have to find out the predicted value and actual value is there. So difference between the predicted value and actual value is loss function, which is explained in the previous video. And the cost function is average or total error of all the data points. Suppose if I am having the 10 data points, we have to calculate a loss for all the 10 data points. The summation of this data point is the cost. Summation of all 10 data points is cost value. So the cost function can be applied here by using least square error method or mean squared error method. Here mean squared error method is applied here. 1 by 2m summation of I equal to 1 to m, between the difference between predicted output and actual output whole square. Then we will get the total cost. With respect to the cost, we can update the parameter by using gradient descent. Gradient descent is one of the optimization approach to update the parameter to increase the accuracy and to reduce the error. Here we are updating the parameter theta value by using the formula theta minus the generalized formula is new theta value is updated with the old theta value minus alpha into dou by dou theta of this is error total cost, right? So this is what we have to use here. And then since we are having the so many theta values, you can apply the theta 0, theta 1, theta 2, etc. When you are applying the gradient descent, here we are using the alpha is the learning rate. We can apply the small learning rate or bigger learning rate. Small learning rate, when you are applying, it will reduce the error step by step until reaching the global minimum. So this is the formula for updating the theta 0, and the theta 0 into here x0 will be available. You look at here, our equation is having theta 0 x0, and when you are updating the parameter 1, we will use x1 feature. So x1 feature I value is here 1. Then when you are updating for the theta 2, then you will get theta 2 minus alpha into 1 by m summation of I equal to 1 to m, then difference between y dash and y whole square, then x2 feature. Here x2 feature will come. Like that, generalized formula will be theta n equal to theta n minus alpha. Actually we will use the j here, theta j equal to theta j into alpha minus dou by dou theta j, here error, and with here xij. So that is what we have given. This is the generalized formula. That is what we want to use in the updating parameters. Then we will reduce the error to increase the accuracy. Thanks for watching.